biconcave, biconcave, planoconvex, and biconvex. Okay? We can group them together. We can create more complex systems. So, for example, I can have a biconvex with a plano concave convex. So I can have something like this, and then I can create systems that are a little more complicated. Okay? But basically, these are like the general general shapes of lenses. These two, we can also call them converging lenses. Or positive lenses. And these two are going to be diverging or negative lenses. Okay, all of them behave a little bit different, and all of them have specific uses. For this class, for the kind of analysis that we're going to be using, there's really no difference between using a planoconcave and a biconcave, and there's no difference between planoconvex and biconvex. So for this class, we are going to assume that we are only working with biconcave and biconvex lenses. Okay? Now, the way a lens works is very similar to the way a prism works. So, in the sense that it's going to have two surfaces, and when light goes through each one of those surfaces, we're going to have some refraction. So, light goes into one surface, there's going to be an angle of refraction, and then it goes to the other one, and then we're going to have refraction again. Okay. We call them thin lenses because the thickness of the lens is smaller compared to the diameter of the lens. Okay? So when we are working with thin lenses, then we can kind of ignore the double refraction and then just assume that this refraction happens in a single stage, just in a single step. So I can draw my lens just as a single surface and then draw it like that. Okay? To differentiate between biconcave and biconvex, what I'm going to do is I'm going to draw like the apex of the lens. So it's going to be, that will be my biconcave, and biconvex will be something like that. Okay. Now, doing the graphical analysis of image formation is not difficult, but there's a particular way of talk about the references of the distances and all that stuff that is a little bit unusual. Many of the theory that we have about lenses was developed by the Greeks and the Egyptians like thousands of years ago, and then there was a big reformation by the French in the 1700s, 1800s. But since then, there's really no much modification. So the methods that we use to talk about the references and the different elements in an optical system, it looks kind of weird, but it's just for historical reasons, because many people were. Okay, so I'm gonna be trying to describe how images are forming. So we need to have a series of references. Okay, so the first reference that we're gonna have is an horizontal reference. And along that line, I'm gonna put all my optical elements. So that reference, that horizontal reference, is called the optical axis. So so this is going to be my optical axis. Okay. Somewhere in the optical axis, I'm going to place a lens, okay, and I'm going to try to create an image with that lens. So I'm going to be working with this bicondylar lens, and I'm going to put my lens somewhere in my optical axis, and the center of the lens, so the center of the lens is going to be along the optical axis. So I'm going to have half the lens above the optical axis, half the lens below the optical axis. So I'm going to have my lens, let's use civilized units here. Okay. And the intersection of the lens with my optical axis, that's going to be my origin. Okay? Now, distances above the optical axis are going to be positive. Distance below the optical axis are going to be negative. Okay? Everything to the left of the lens is called the object space. And to the left, sorry, to the right is going to be the image space. Okay? And when we are working with imaging systems, we're going to have objects, and we're going to have images of the objects. Okay? And depending if you are talking about the position of the object or the position of the image, you're going to be using different frame of references. Okay? So when you are working with about objects, this is going to be your origin. Okay, so this is going to be your origin, and then your positive distances are going to be growing to the right, to the left. Okay, so this is going to be positive distances, and these are going to be negative. This is going to be your origin. Okay, and when you're talking about images and you're trying to find out what is the position of the image, it's going to be the opposite. You're going to have positive distance to the right and negative distance to the left of the lens. So we have the lens, we have my optical axis, and it's going to grow like this. So I'm going to have positive distance and negative distance. Okay. Now, I'm going to have a light source somewhere in the object space, and it's so far away that all the light coming from that light source is going to be parallel to the optical axis. Okay, so all the light coming in are going to be parallel to the optical axis, and so I'm going to have a bunch of rays parallel to each other. So they're going to be like this. Now, we call these lenses converging lenses because when you have light that is parallel to the optical axis, all that light is going to be converging into a single point on the optical axis. Okay? So, this. which all rays converge, that's called the focal point. This is the focal point. And the distance from the lens to the focal point is called the focal length. So the distance from the lens to the focal point, this is the focal length. Okay. Now, the system is symmetric. The lens is completely symmetric, so it doesn't matter which direction the light comes. It should behave the same way. We have parallel rays coming from the right, propagating to the left. If they're parallel, they're gonna focus in a single point here. So we have a focal point to the left, we have a focal point to the right, we're gonna have a focal point on the left. So here, I'm gonna have another focal point. And here, again, is gonna be my focal length. Okay, it is the same on both sides. So if you have 10 centimeters focal length on one side, you're gonna have 10 centimeters focal length on the other side. Okay? These are called positive lenses because the focal length is gonna be positive. And they're negative lenses because we're going to have negative focal length. Okay, so if they tell you that you have a lens with a focal length of 20 centimeters, you know there's going to be biconcave. If they tell you that you're going to have a focal length of minus 50 centimeters, you know that you're going to have a biconvex lens. Okay. Sometimes you're gonna see that this is the object focal point, and this is gonna be the image focal point, just to distinguish which one are you talking about, okay? I think that's it, okay? Make sense? Okay, so now I'm gonna use these elements and these rays to create an image, okay? So I'm gonna delete this stuff. Keep my focal point. And focal point. So let's say that I have an object, and I normally will draw an elephant, or a turtle, or a cat, but just to simplify it right now, I'm just going to be a very boring arrow. Okay. So you can imagine that you have a light source. The light source hits your object, and then you're going to have a bunch of rays just being reflected at every single direction. Okay? Of all those thousands of rays, there's going to be just a limited number that are going to be captured by your lens, and those are the ones that are going to be creating the image. Okay? So, of all those thousands and thousands of rays, I'm just going to pick 3 rays, and those are called the principal rays. So, I'm gonna start from the top of my object, and the first principal ray is gonna go parallel to the optical axis. And what happens to light when it's parallel to the optical axis?
It goes straight.
It goes through, it bends, and what else? Where it goes through? It goes through the focal point, right? So it's gonna bend and it's gonna go through the focal point. So this is gonna bend and it's gonna go through the focal point. Okay? My second principal ray is gonna start again from the same point, and now it's gonna go through the origin of my system. So it's gonna go through the intersection of the lens and the optical axis. Okay, and that ray, it's gonna get refracted twice on the interfaces of the lens, but it just comes out at the same angle, so you just keep going straight. So this one is just gonna come out straight like this. Okay, and the third principal ray is gonna go from the top of my object, and it's gonna go through the object focal point. Okay? It's gonna go through my lens and it's gonna come out parallel to the optical axis. Oops, this one doesn't appear one. Okay, and that point of intersection, that's the image of my object. Okay, so this is the top of the object. Now the top of the object is going to be there. I can do the same thing, trace these principal rays from every single position of my object, and I will be finding that intersection on this plane. And at the end, I have an image that's going to look like this. In this case, I think it just turned out that way. It doesn't necessarily happen all the time. Just in this case, it's just turned out that way. Sometimes you're gonna have an image that is bigger. Sometimes you can have an image that's smaller. I'm not, even though it's a graphic method, I'm not being careful, and I don't have a graphic or anything. So
Mine turned out to be bigger.
yeah,
And it's just because I was not using the roller.
yeah, now, the distance from the lens to the object. This is the distance to the object, this wall. And the distance from the lens to the image is the distance to the image. Very, very brilliant. Okay, now remember, we are measuring distance depending if we are talking about the object or we are talking about the image. So the object is in the object space, so this distance VO is gonna be positive, okay? The image is in the image space, so this distance is gonna be positive, okay? If we have the image somewhere around here, it will be a negative distance. If we have the object somewhere around here, we will have a negative distance to the object. by convention, we always place the object at a positive distance from the lens, just to simplify some of the calculations. Okay? Now, one of the things that we can do is to calculate the magnification of the object. Aubrey, you did something to your hair. We can calculate the magnification of the object, okay? There are two ways that we can calculate the magnification. Sorry.
That's okay.
You can look at the difference in height, so you can compare the height of the image to the height of the object. Just be careful that if your image is below the axis, this is gonna be a negative distance, okay? So, let's see if it works. So my image, sorry, my object is around 8 centimeters, and my image is 5 centimeters. So the magnification is the height of the image over the height of the object. So this would be minus 5 centimeters over 8 centimeters. So we're gonna have an image that is smaller than the object. So that's like 0.6. So
Negative?
negative. Okay, and that negative, what it indicates is that the orientation of the object and the orientation of the image, they're gonna be flipped, they're gonna change. That's all that it means. The other way that we can calculate the magnification is by comparing the distance to the object and the distance to the image. Okay? So the equation will be minus d sub I over d sub O. Okay? So in this case, my two distances are gonna be positive. I'm just gonna add that negative. So my distance to the image is gonna be 47 centimeters. And my distance to the object is gonna be 58 centimeters. This one, it didn't turn out so well. In this case, we get different values because I'm not very careful with the dimensions, but usually you get the same values regardless of what equation you use. Yes?
So what tells you if it's bigger or smaller?
If you have a magnification bigger than 1, it's gonna be magnified. If it's smaller than 1, it's gonna be reduced. Yes?
So what does the negative sign in the second equation mean?
You just need to add that because you are working with positive distances. So to indicate if it's flip or not, you need to add that negative. That's the way the equation is.
So I'm trying to think about it, but it's not making sense.
Don't think it, just accept it, embrace it. It is what it is. Sometimes physics is like that, so just accept it.
I mean, the first one makes sense, the fact that the image is flipped, so you gotta put it there. Like, if you're using the object distance and the image distance, you put negative, does that mean you're not on the same side? Or sometimes,
If you use a positive, you don't add that, that's negative side. You will have a magnification that, for example, is negative 6.25, and then you use the equation and it will give you a magnification that's positive 6.25. So there's a mismatch between the two of them. So you need to add this negative sign to account for that flip of the distance of the image.